The indefinite integral symbol has some basic properties, just like the definite integral symbol had basic properties. It doesn't have as many, though. So, for example, properties of indefinite integral. So, if we have a sum of two functions, or a difference, won't matter, as an integrand, then just like the definite integral had the sum difference property, so too does the indefinite integral. So we can apply the integral symbol, right, the antiderivative indefinite integral symbol to both these functions separately, x dx, and plus or minus the integral of g of x dx. This will hold true. And again, all it's saying is if you take the antiderivative of this entirety at once, it would be the same as taking the indefinite integral, right, taking the antiderivative of each one separately and adding after the fact, or subtracting. There's our sum difference property that so many of our operators have had in this textbook. And the other one, hopefully you're suspecting it by now, the constant multiple property. If I have a constant multiple on a function inside the integrand, I want to take its antiderivative. Well, since derivatives are allowed to have constant multiples move outside the derivative symbol, the derivative operator, so too antiderivatives have the same property, because they're just the reverse procedure of any derivative. So the constant multiple comes on the outside, and you can simply take the antiderivative of the variable part of the function and then multiply by that same constant after the fact. So therefore, this is our always reoccurring constant multiple property. And now some specific rules that are going to come up a lot and will help us to evaluate these antiderivatives and ultimately definite integrals, as well as these indefinite integrals. So, for instance, extremely important one is, what do I do with a power function? I want to take its antiderivative. Now we know when we take a derivative, let's think about this very quickly. When I take the derivative of a power function, right, the process, the mechanical process, you might say, that goes into this is I take the current power and I multiply it onto the exponential expression here. I should say power function here, and we get n minus 1 for the new exponent. So the process is twofold. I take the current power and I multiply it onto the power function, and I simultaneously, or I shouldn't say simultaneously, but secondarily, you might say, lower the power by 1. If we were to invert this process, just like when you want to invert a function, right, find the inverse of a function, you do the opposite operations in the opposite order. Okay? So if we do the opposite operations, again, there are two, right, in the opposite order, then according to that, we made a rule for that. Right? Since the second thing I did was to lower the power by 1, that means here, when I'm doing the antiderivative, I'm doing this process in reverse, I should up the power by 1. Okay? So I should have x to the n plus 1 to start with. Okay? That would be the first move here, because lowering the power by 1 is the last move here. Okay? So the first move here was multiplying by the original power. So here, the last move done, the second move done, should be to divide off by that power. Okay? So the book would write this as over n plus 1. I'm just going to write 1 over n plus 1 out here. Sometimes it helps to think about it like that more than being over n plus 1, especially when you have fractional exponents. Okay, so there's the rule. Let's write plus c here, so we get the general antiderivative. So there's our rule for power functions. This is the power rule for antiderivatives. Now there's not a corresponding rule in antiderivative land for all the derivative rules that you already know. Some of them exist, some of them don't. This one certainly has a corresponding power rule, and we just exhibited it, and you want to make sure to be aware of it as quickly as possible and be able to use it. It comes up all the time. Other rules are more visually obvious, you might say. For instance, I already mentioned that the antiderivative of e to the x is, of course, e to the x. But what about the antiderivative of 1 on x? What should it be? We know when we take the derivative of natural log, we get 1 on x. So therefore, the antiderivative of 1 on x should be natural log. It's just a visual thing, right? You see this in here, and you know it's really a knowledge of derivatives that gives you the clue to the antiderivatives. You know that this is the derivative of something. What is it? Well, natural log of x. I'm just going to put plus c to complete the general antiderivative. Now, this also has a special feature, and that is we're going to widen, in a sense, the domain of our natural log here. We're going to put an absolute value on the input x here. And this is the widest domained antiderivative for 1 on x. Natural log of x without the absolute value is also true, but it doesn't have the widest domain that it possibly could and still be true. So therefore, we're going to include this so that the natural log is as general as possible for this particular antiderivative.